There is Fourier series on the homework. All right, but that is the Fourier series stuff is basically going to be on the next exam. Okay, so it's not on this exam. The material that is on exam 2, which is a week from today, that material is going to be differential equations. All right, and it's going to be like the function manipulation stuff that's on the current homework. Right. And there'll be a practice exam, like I said. All right, I'll give you guys not a full probably 4 or 5 problems, but at least 2 or 3 to give you a sense of what they'll look like. Okay. If you look at the problems on, the homework, problems 1 and 2 minus the MATLAB are pretty similar to what you would have. Something like problem 6, problem 4 and 5. Those are pretty much what I would expect to see on the. So I'm talking about the current homework when I mentioned that. Yeah. All right. So yeah. So Fourier series, this stuff is on the homework. It's not going to be on the exam. Okay. All right. So if you look in the sections in the book here, it's section 9.1 and then 9.2. Look at my announcement from yesterday. It talks about some sections in the book that are helpful for what's on the current homework, okay, which are all in chapter 2. Okay. All right. So in particular, I say 9.1 and 9.2. It's really mostly all 9.1. And I'll be honest with you, if you go in there, there's a lot of formulas. So I've got some equation sheets that kind of distill down the important equations because you don't need to know all that stuff. All right. If you want to know it, that's different. That's up to you, right? But I'm trying to distill it down to the things that are really important. So last time I introduced this idea of Fourier series. It's basically, all right, so the whole thing, we talked about dynamic systems, the stuff coming up on the next exam, all about differential equations. Okay. Differential equations, if I have a dynamic system means what? What the heck what do I mean when I say dynamic system? What's the meaning of that? What's that? Changes with time. So if I had, if this circuit right here had 2 resistors instead of a resistor and capacitor, it would not be a dynamic system. I'd turn on the power switch and the voltages and the currents everywhere would immediately get to their final value. All right. But once I have a capacitor, the capacitor fights the change. Same thing with an inductor, fights the change. Right. So what we said is with this, I got to write a differential equation. This is the differential equation we write. We could get that from KVL. That means I get a transient piece and a steady state piece. Okay. Now I wrote out here already, what does the steady state look like? Well, if I had a cosine going in, it's scaled and shifted. All right. As we've seen, and you're doing the homework again right now, this whole thing is annoying to do, right? It's annoying to go through this process of writing a differential equation and solving this. For the most part, we don't really care about the transient response, okay? What do we say we could do instead? What's the whole idea of, if I have a sine wave, it's special. If I have a sine wave, what's so special about putting a sine wave as my input into this differential equation? What happens with the sine wave? Like if I guessed, what we ended up saying was, and this is what you're doing right now, basically this guy is my final value here is the real part of a e to the j phi e to the j omega t. If I guessed that whole thing, which is what you should be doing on problem 1, I think, on the homework right now. If I guess that, what's the nice thing about that equation? Get rid of the time piece. That leads into this idea of impedance, right? So what we did was we basically said, okay, the fact that my input looks like this means my output looks like this. So they have different amplitudes and different phases, but their frequencies are the same, right? Basically meant that I could just use these whole phasor things here, just a magnitude and an angle, right? And I didn't have to do the differential equation. If I do that, basically I'm saying, you know what? I really don't care about the transient response, okay? For the most part, very often that's true. I don't care about the transient response. I just do the steady state stuff. And if I do that and I said, okay, well, I wanted to use phasor analysis or impedance analysis, how would I do that here? So in this case, V out, I'd solve for the phasor of V out in terms of V in. So do I have to write a differential equation if I want to solve for the phasor of V out? No, I don't, right? What would I write here in this case? If I knew the phasor of V in, how would I figure out the phasor of V out? What would you do? What's that? Voltage division, right? So and again, this is not something on test here, but I would have the impedance of the capacitor over the total thing times the phasor for V in. And this would tell me basically the angle and the magnitude of this would tell me what the magnitude and the angle are here and here. Okay. All right. It's a stranger approach because we're using basically complex numbers, but we're getting rid of the time dependence, which gets rid of the calculus. Basically, we're turning a calculus problem into an algebra problem, an ugly algebra problem, but it's a lot better than a calculus problem. It's a pretty grungy calculus problem. All right. This only works for what type of input? What do I have to make this work? Have to have a sine wave. All right. Most waveforms are not. All right. So I talked about this last time. Periodic waveform. This is a very common one, right? This is a clock signal. This is a digital signal right here. I put a digital signal into this circuit. Can I use impedance analysis? No, can't. Right? Not straight away, at least. I'd have to write the differential equation for this one. But what we said last time is the whole idea is the whole idea of a Fourier series is that any waveform that's periodic is expressed as a sum of harmonically related sine waves. What I used here, a more mathematical term, a linear combination of periodic basis functions. In other words, I can think of these, when I say basis functions, basically meaning little scaled and shifted versions that I can put together and add up to create this guy. All right. So if you think about it like that, this statement, the fact that I have a summation, means that if this square wave was a voltage source, these two circuits, the one on the left here and the one on the right, are the exact same circuit. Okay. Now I could use impedance, couldn't I? What if I wanted to hook this up to my circuit, my RC circuit? How could I use impedance analysis with this? What other trick would I need? What circuit analysis tool would allow me to use impedance analysis? Superposition. I'd have to analyze one by one by one. Okay. What we need to determine is what are these things like these little coefficients here, because those are special. Those coefficients need to be determined in such a way that those cosines fit inside of that square wave and exactly equal it. All right, so we got to figure out how to compute those values. All right, so he said this is a pretty useful thing to do, and I said it's very commonly used. I gave this example last time, but it's the same sort of thing. If you're doing robotics, when you drive a motor in a robot, you drive it with a square wave, and you call it a PWM, pulse width modulation. Example I gave here, this is where a microcontroller would basically generate this voltage V sub I. My example here is if I had this thing I called an inverter. Basically, some circuit that could take. So I wrote the word PV. Some of you may not know what that means. Photovoltaic, so a solar panel. I take a solar panel and I hook it up to the grid, and the grid looks sinusoidal. I somehow have to take DC, which is what comes out of that panel, and I got to turn it into AC. So turning a DC waveform into a sine wave is not a hard process. Basically, there's just some switches inside this box that make that happen. Right. And there's a microcontroller that tells the switches how to turn on and turn off. And the voltage they create is this sort of this kind of square wave, which with what looks like it's got changing periods over time. If I take that waveform and I put it through a circuit, what it comes out as is a pure sine wave. All right. And the circuit basically is removing some of those, what we called last time, harmonic frequencies. All right, now that's a little bit beyond where we're ready to talk about now, but you can maybe begin to see where project 2 might be going. All right, is how do we apply the thinking that this sort of thought process enables? Okay. All right. So last time and I want to recall this and go back to it. So sine waves are really important for this reason, right? The fact that basically any periodic waveform is a sum of sine waves. And that's what we have all the time. Sine waves or periodic waveforms. Those are really common. So they're really important tools. So basically what we said last time is, and we said this before, I basically have 4 different ways of trying to relate sine wave. In other words, all of these things right here, I say approach 1, 2, 3, and 4 are all equivalent to each other, right? So if I had a single waveform, I could represent it each of these 4 different ways. Okay. All right. So this is the most common one. This is what you say in circuits. If I put a sine wave input into a circuit, I get a sine wave output that has a phase shift and an angle, or phase shift and an amplitude. This can be written as the sum of a cosine and a sine. Now notice there's no shift here. There's no phase shift. It's just the sum of a cosine and a sine at the same frequency. How did I get last time from this top one, approach 1, to approach 2? What did I have to do to get from the first one to the second one? Trig identity. Okay. And what if we go through carefully, this is really all you need. Like I said, there's a lot of formulas there in that first chapter, or that first section of chapter 9, but this summarizes them here. All right. And I will probably create on the Canvas page kind of a set of sort of helpful summaries, so you don't have to just necessarily go and try to pull this out of the notes. All right. But basically, I can relate all of these things together. And we're going to look at an example here. This is pretty similar to the problems that you have in problem 7 on the current homework. All right. This is stuff you guys know how to do, or should know how to do. Okay. We're just putting it together in kind of a new way. How do I get from this top one to number 3? What the heck is going on in number 3 there? What's that?
Euler's identity.
Euler's identity. So e to the j omega t, what does that look like? How do I draw e to the j omega t? I can't draw that like in a regular way, right? So I have a real axis and imaginary axis in the complex plane. And e to the j omega t is a vector, right? And what does that vector do as time goes on? Rotates. In which direction does it rotate? What's that? Well, if it's e to the j omega t, it rotates clockwise. Sorry, counterclockwise. A positive direction. Positive direction is counterclockwise. And then his buddy, the conjugate, is down here. This is e to the minus j omega t, and this is e to the j omega t. The summation of those is always a real number. And if I watched it like we did last time, you'll just see it going back and forth on the real axis. Okay. Then this last piece here says if I take the real part of just one vector, that also is related to each other. All right. All 3 of those things are related. The nice thing about, so people are like, well, this is, you're smoking something. Why would this sort of complex imaginary thing be useful? Because the calculus associated with the sine and cosine together is the calculus and the trig, and it's a mess. All right. It becomes a lot simpler to be able to use the complex number piece. So we're going to use that a lot because it simplifies the calculus, gets a lot of the calculus out of the picture. All right. So basically what I say is I look at it this way, and you're going to see some more examples of this over the next couple of lectures. But basically, if I look at this, what I call the shifted cosine. So just to give it a name, this guy is what I call shifted cosine, because it's a cosine that is shifted by phi, right? And then this guy is what I call sine cosine. And then this guy is my Euler's identity. Basically, if I look at those approaches, they're all related to each other. And if I know any one of them, I can pretty easily move back and forth into the other 2. All right, so that's going to become important, particularly on Wednesday when we start really trying to get into calculating some of the Fourier series stuff. All right, so let's look at an example. All right, on the homework, problem 7 basically asks you to put something like this, to put it into all of those different forms. So the shifted cosine, So let me just write it out. So it asks us to put it into the C cosine omega t plus phi. It asks me to put it into A cosine omega t plus B sine omega t and alpha 1 e to the j omega t and alpha minus 1 e to the minus j omega t. And it asks for the phasor c e to the j phi e to the j omega t. So it's asking specifically for that phasor. Okay. All right. So my solving approach here is let's choose one of those that I can kind of recognize, and then let's use the formulas to convert between them. Okay. So of those three, which one do you recognize there? Second one. All right. So looking at this guy right here, it looks like he's in this form. So what is A and what is B? That's annoying. What's A and what's B? Looks like 10 and 5. Okay. So I can see right off the bat what that form is, right? If I already have that form. So easiest one for me to go to next. So the way I look at this is, okay, I've got this sine cosine. Well, there's a set of formulas through the trig identities that let me move to the shifted cosine. So let's do the shifted cosine next. So we've got this one. We've got the sine cosine. That's done. Now I want to do the shifted cosine. How do I do that? How do I do that? How do I relate those? Well, if I go back through my trig identity, I had the relationships I have right here. Right? If I know A and I know B, I can use these two formulas right here to relate everything. Okay. So the way I look at this is I've got A equals C cosine phi and B equals minus C cosine phi. Sorry, minus C sine phi. Right? If I did A squared plus B squared, what's that give me? So if I did A squared plus B squared square root, what would that be? BC, right? If you go through the math on that, it's not hard to show, right? I'd end up with a sine squared plus a cosine squared, which is 1. So I get C from that. Okay. Now, how do I get the angle? If I just look at this right here, you should be able to see how to get that, right? If I do B over A, what's B over A going to be equal to in this case? Negative, well, so yeah, it would be negative C sine phi over C cosine phi, which if you're paying attention with your with your trig, minus tan phi. Okay. So with A and B, I have everything I need in these two equations to solve for that. Okay. Now, where should I go next? Well, I guess I can do this one next, the phasor, right? The phasor would just simply be, once I know a number for C, I just say C is C, and so C e to the j phi, I just put those together, right? I can solve these two expressions here to get a number for C and phi. All right, now what about the Euler's identity piece? Oh, so that's this one. What would I do to get that one? I go back to that formula sheet again, but if I know how to relate this guy, what I end up going back to, if I go to my formula sheet here, alpha 1 and alpha minus 1. What does this mean? Alpha minus 1. Yeah, the magnitude is C over 2 for both of them. Okay. The heck does this mean? Alpha minus 1 equals alpha 1 asterisk. What the heck is that?
Alpha minus 1 is
conjugate. Yeah, they're conjugates of each other. So basically what that ends up saying is alpha 1 is C over 2 e to the j phi, and alpha minus 1 is c over 2 e to the minus j phi. All right, now, here's how I would do that in MATLAB. Here's what I did. So here's my code. This is my code for plotting them, I guess. But what did I do in my code? My code basically just does this. I define A and B, and then I basically just run these guys, and then this and this, and then this is my phasor. So what I did here was I basically tried to plot them. All right. And so I actually got on that graph right there, I have all four versions plotted on top of each other, all for the same time vector. So a couple of things to bear in mind for you guys when you look at trying to plot this. So notice, remember, when I have cosine, cosine assumes what type of angle, what unit for my angle? Radians, right? So notice what I did. My phi was in degrees, so I converted it to radians, okay? This form here, okay, I got no phase angle to worry about. And then I have, so this is my alpha 1 and my alpha minus 1, okay? And then this is the fourth version. Now, what I probably should also give you, maybe what I'll do when I upload this is the code I wrote for these things too, so you guys can see it, right? How I actually calculated those as well, okay? It should be pretty straightforward after you've done it. All right, and you've kind of already done this sort of thing before, all right? So it's not that, hopefully it shouldn't be that bad, okay? All right, but you can see there's four graphs on top of each other right there. So there's several things there. Each of the ways of doing this can be useful for some things and not for others. All right, so we don't need to say too much more about that, but this should help you as we get into the Fourier series stuff where it starts to get a little more complicated. All right, so now if I have something like this is where it gets interesting. So this guy is periodic. All right, so to say that this waveform is periodic, what's my definition of periodic? What's true about a periodic wave? Repeats every period. So how do I write that math-wise? Yeah, basically the value now at time little t is equal to the value of t plus big T. And technically it's equal to the value at little t plus 2 times t and little t plus 3 times t, right? But this is our definition of a repeating waveform. Right? If it repeats with the period t. If I have this input, the whole Fourier series idea is that somehow I can add up a bunch of sine waves with related frequencies and force them to fit into and add up to that square wave. Okay. So we got a couple of things that we got to work through to try to figure that out, but that's basically the idea. So in this case, the way I look at this is I say, well, if I took a sine wave, and I specifically mean a sine function, I should, so the word sine of, I took sine and tried to fit it in here like this. Right? That sine perfectly lines up with this thing. Now, to get it to fit closer, what would I have to do? Raise it up, right? So I got to add a constant. So basically, this is where we started with last time. I said I got a different kind of square wave that starts at 2, goes to 0, then it's going to go back to 2, then it's going to go back to 0, then it's going to go back to 2, and keep repeating. So I start out with this guy right here, okay? And then you said I had to shift it up. How much would I have to shift this up to fit inside of that box? I'd have to add 1 to it, right? So here I call this guy B1 sine omega t plus 1. All right, so you can see they kind of fit in together with each other. But obviously that sine wave and square wave, they're not the same, right? And I don't know what the heck B1 is. B1 is some amplitude. All right, now what we do in Fourier analysis is we try to figure out what is B1. All right, we try to figure out what that magnitude is. So yeah, I guess the axis stops at a different value here. The square wave here is in blue. So the square wave is here. Yeah. Let me try to outline that more clearly. This is the square wave. So I shifted the sine wave up. So if you look, the sine wave here is its valley here is somewhere between -1 and -1.5. It's shifting up, so it's a little bit between 0 and -0.5. So if you look at it, and I say I shifted it by 1, you can see this guy is centered around 0. Now it's centered around 1. So I added 1 to that. All right, I shifted that up. Sometimes in circuits we call that we biased it. We kicked it up a little bit. Okay. Now that's not good enough. So what I want to do is I can keep adding more sine waves. What's true about the sine waves that I add to it? What did I say last time? How are they related to each other? The sine waves that we add to it. They're harmonic. What's that mean? And we're going to talk more about that if you don't remember. You probably don't. What does it mean to say that they're harmonics?
They had to be multiples of each other. In this case, they had to be odd multiples of each other.
Yeah, they have to be multiples, integer multiples specifically of each other. And it turns out for this particular waveform, it has to be odd integers. Yeah. So if I do this guy right here, what I actually have now is this is 1 plus B1 sine omega t. So just like I had before, but I've added to it some amount of what I call the third harmonic. All right, so this guy, I gave this term right here a name. What was the name I gave to this guy? He has the same exact frequency as the underlying original wave. I called this the fundamental term, or sometimes we'll just say first harmonic. This guy right here is what I call third harmonic. Okay, this stuff happens all the time. All right, in the real world, we have square waves. Or if I look at the wall outlet, I'll see that I have 60 hertz plus 180 hertz, which is what? So the voltage at the wall is 60 hertz. What's 180 hertz? Which harmonic would that be? The third. All right. So these things happen in the real world, that I get those sorts of waveforms. Now to get that, to sort of better approximate that square wave, I got to keep adding stuff to it. So the next one I added here, this guy is 1 plus B1 sine omega t plus B3 sine 3 omega t plus B5. So I added what I call fifth harmonic now. And you can see if I go through the progression, right, this one, you know, the only thing that's matching about those two is they have the same frequency. One fits kind of into the other. This guy fits better. This guy fits better still. This guy fits better still. Now when he's got fifth harmonic. Here I have all the way up to n equals 99. So I have up to 99 harmonics. Now I can see that summation is starting to look pretty close. But what's important is the amplitudes here have to be just right to make that work. Okay, and the thing we got to do is figure out how we get those amplitudes. Right, there's a whole mathematical procedure for doing that. And this is the kind of thing, you know, if you've ever heard of you guys use oscilloscopes in the lab, but you know the other tool I don't think you use in the lab, but a spectrum analyzer. Basically, it's where I take a waveform like that square wave and it tells me the harmonics that are there. All right, so there's a lot of tools that'll tell you that kind of thing. Okay. All right, so what we learned from this eventually is a way to take, if I have a voltage source in particular, that is a square wave, I can learn to model it as this sum of individual harmonic frequencies. All right, so this is the reason why we went back and look at those 4 approaches, right? Is there's basically 3 representations of the Fourier series, okay? All of them are talked about. The one that's used most commonly in ECE stuff is this guy here, the complex form. All right. There is also the sine cosine version and the shifted cosine version. You are only ever really going to solve for the alpha n values here. And then you're going to use those formulas that I gave you here. All right. You're going to use these formulas to relate the alphas to the A's, the B's, and the C's. All right, because it's the calculus, as we'll see, the calculus is ugly to figure out A, B, and C. All right. Now, the key thing is the Fourier series can represent any periodic waveform. All right. Any periodic waveform can be represented that way. Now, if I look at a couple of things here, there's some things that are going to kind of bake your noodle a little bit, right? One of them is this over 2 piece, all right, here. The other thing that'll probably mess you up a little bit is if, first of all, I'm not sure how comfortable everybody is looking at a summation, okay? If I'm looking at a summation, this guy is a summation that runs from n equal 1 to infinity, okay? So if I'm running from n equal 1 to infinity, how's that different than this guy over here? The complex version down there. How are they different? Yeah, the complex version basically has twice as many coefficients in it. Why is that? Why does the complex version, why does this one have twice as many components as this? So we'll see this as we go through an example here. But if I had a single sine wave, for instance, right? If I had, let's say, 4 cosine 2t plus 45 degrees, right? What's that look like if I go into the complex form of it? What is this in complex form? How many vectors does it take to give me that? 2 vectors summed up. That's why this guy has twice as many points. All right. So we'll have to bear that in mind as we go through our examples here. All right. So the most common one from like a math perspective is usually this one. All right. But that's not the one we're going to try to manipulate calculus wise. All right. So we're going to do the calculus on Wednesday to really kind of go through it. We're not going to mess with this one really so much with the calculus. What we're going to do is get the alpha values and relate the alpha values to these coefficients. All right, we'll make that make more sense as we go. All right, the way that I try to visualize this, that's helpful. Some of you guys may not be all that comfortable with what this says mathematically here. F of t, this guy is my f of t right here. All right, this square wave. The way that I think about this is if you could create this square wave by getting a bunch of sine and cosine waves at these harmonically related frequencies, figuring out how much of each one, and then adding them all together. So the way this picture sort of works here is it says like this, right? So what is this waveform right here? A1. This is referring to what I call the first harmonic, right? So what is this waveform, this one right here in this graph? What does that look like? I know the y-axis label is small even from where I'm standing. Maybe it's bigger where you are actually. It's going between 1 and -1, I'll tell you that. So the maximum value here is 1, the minimum value is -1. What is this guy? What is this wave here? Cosine. What is this one here? So this one's cosine. What's this one? Sine. What's this one beneath it? It's a cosine, but particularly if I call this one cosine omega t, what is this one here? Cosine omega 2t or 2 omega t. Now, how can you tell? So that guy has twice the frequency. How can you tell visually that has twice the frequency? Well, and specifically, if I look at how long it takes to go through the period of the first waveform, this guy goes through 2 cycles when the first one goes through 1. Right? So this guy varied twice in the time it took this guy to vary once. That means he's varying twice as fast. All right. This guy here would be sine of 2 omega t. Also twice as fast, but it's a sine. What's the one here? This guy goes through how many periods in one period of the top one? 3. Right? So I can see 1 period, 2 periods, 3 periods, right? That. All right. And then same for this guy on the bottom. Okay. So what I see is this, right? I got to figure out how much of each of these, each one, how much cosine do I put in? How much sine do I put in? How much cosine 2 omega t do I put in? How much sine 2 omega t do I put in? All right. So based on what I worked out, again, we'll figure this out later, but basically at each of the harmonics, so at B1, if you go through the math, it's 4 over pi. And if you do it at the third harmonic, it's 4 over 3 pi. And if you keep going for the general nth harmonic, it's 4 over n pi. All right. So basically what that says is, how much cosine did I add in there? To create this square wave, right? So here, how much cosine did I add in? Did I add any cosine in? No. So that means that this A1 value is 0. So I don't add any of this. The way I think of these coefficients is they're like knobs, right? So I have my basic values here. I have my cosine 2 omega t, my sine 2 omega t. And then I have these knobs that control how much of them I need to add up to the total waveform. Okay. So I'm saying I don't need any cosine to do that, but I do need this much of sine. And I don't need any of that, but I do need, and I don't have any second harmonic. And this guy, I need 0 of that, but I also need 4 over 3 pi of this. And I keep going. All right, now we got to figure out, how do we get those values? All right, that's what we're trying to figure out. But the main thing is you first want to be able to visualize this. What this thing is saying is that for any given value of t, if I calculate the total function for any given value of t, so at the value of time right here, this is telling me how much of each one of these things contributes to the total sum. All right, so some basic definitions that we got to deal with. All right, so the first thing is here, the fundamental period. I said it's the smallest period over which the waveform repeats. All right. This is tricky. This is important. The smallest period over which it repeats. I mean, technically, right? If I looked at cosine, how many times does cosine repeat? The cosine of omega t, how many times does that repeat? Infinitely many. Yeah, it repeats every period. Okay. So it's the smallest time period over which this waveform repeats. I call that my fundamental period. All right. Then I have my fundamental frequency, which is 1 over that. And then what I say is that all of the frequencies inside there are n times that frequency. And I call that the nth harmonic frequency. And I have this thing I call the harmonic number that tells me, am I dealing with the n equal 1 first harmonic, n equal 2 second harmonic? The other term I used here, I call the DC term, right? So the DC term is this guy. All right, what frequency does that guy have? 0. Why? Because he's got a 0 subscript. If I have a constant, how much does a constant vary? Doesn't vary at all. All right, so we say it has no variation, never varies, 0 frequency. Okay, so this guy, sometimes I call it the DC term or the average term. Okay, we use the term DC because it's the average value of the waveform, which we'll show. Okay. All right. So these are some terms we're going to keep using. All right. So those are our basic definitions of those. All right. So now to approach these problems, like what you have on at the very end of homework 6 is kind of where I can look at a waveform and you can figure out those coefficients by inspection. All right, so the basic thing we start with when we start introducing Fourier series, we say, okay, I give you a periodic waveform. And what you have to do is you have to look at that periodic waveform and you have to figure out what are the coefficients. Okay, how do I take those cosines and sines and kind of put them together to create that waveform? And that waveform I have right there, I said last time, where did that come from? Where did I measure that? One of the outlets. Basically, your laptop, if it's plugged in right now, is plugged into that junk. Okay, so it's supposedly you're getting a sine wave from the utility. All right. And Duke probably is giving UNCC a sine wave. And UNCC has turned it into sort of some sort of, if I cut it off, it looks like Darth Vader's head or something, right? It's turned it into some sort of a strange looking shape. Okay. If I have that, what I need to do is I can solve for the coefficients using calculus. That's what I'm calling this sort of type 2 approach. But to get ourselves comfortable with it at first, we're going to just do it by inspection. So I want to try to look at a waveform and I want to try to figure out what the coefficients are. When I say look at a waveform, I'm going to look at one like this, all right, where I've given you basically a function for it, and you got to work through that function. Okay, so this inspection process, I've got 3 basic steps for trying to do this. So the first is I want to be able to look at the function I'm given, and I want to be able to figure out what the fundamental period or frequency is, right? Because everything builds from that. I got to know what the fundamental frequency is, and then I got to figure out, essentially once I know that, then I have to figure out which harmonics are actually present in the waveform. And then what I got to do is I got to figure out which coefficients do I have at each frequency. And then if it's based on the problems I give you, I'm always going to want you to do A, B, C, phi, alpha, and alpha's conjugate. All right, so you're going to be figuring out all of those. Based on the waveform I give you, you'll figure out which one makes the most sense. And then you convert between the forms. Okay, so here's the ugly guy that we're given. All right, this is a periodic waveform. How can I tell this is a periodic waveform? Because it repeats, right? No, I said the smallest period over which this repeats. Where's the easiest place to see that here? What's that? Where's the easiest place to see the repeating here? Yeah, probably at the peaks or at the bottoms, right? So like when my mind goes to here and here. How long does it take to go between those peaks? Right, so there's the distance there. That's the smallest period over which it repeats. You could also say, well, if I went a little bit further, it would repeat again, right? But that's the shortest time it takes for it to repeat. Now, to figure that out, there's a couple of ways to go through that step. One of them would be to try to plot the waveform. So what I did was I plot the waveform, and I basically, in MATLAB, I measured the amount of time it took to get from one peak to the next. So I don't think I can zoom in on that. If you look at this, this is basically -5 milliseconds and -1 millisecond. So the time between those, from -5 to -1, what's the time between those? What's the distance between -5 and -1? What's that? 4, right? So this guy, the period here is 4 milliseconds. All right. So that's my fundamental period. And we write that with a little 0, all right, subscript. And that means the fundamental frequency is 1 over that. So F naught is 1 over 4 milliseconds, or if you do that math, 250 hertz. Okay. And again, most engineers, when you go to work on a microprocessor, right? You go to Intel and you're talking about your microprocessor, you're not going to say, oh, the frequency is 6.28 gigaradians per second, right? You're going to say it's 1 gigahertz, right? And no one's going to say a frequency, and nobody's going to say the wall outlet's at 200 or 377 radians per second. They're going to say it's 60 hertz, okay? So I'm going to speak in terms of hertz, although you plug it into the sine wave in terms of radians per second. Okay. So here I see that guy's 250 hertz. Now that's one way to do it, is to measure it like I did. All right. I'm an experimental person, so I like to think in terms of just, well, what would it look like if I measured it? All right. But if I gave you sort of this function right here, okay, how would I go and do it from there? Anybody know what's if I've been given some sine waves like this, and I want to figure out the fundamental frequency. Some of you may know. Anybody know? It's the greatest common divisor, something you probably haven't thought about since like middle school or something like that. But the greatest common divisor between two numbers. All right, so the way to figure that out in this particular case, so I've given you, there's 1, 2, 3, 4 pieces to this guy. So the greatest common divisor of the cosine and sine terms. So what I say is, if I look at this, my frequencies are 1000, 1750, and 1500. So in MATLAB, the greatest common divisor can only be computed for two numbers. So what I did was I took the greatest common divisor of 1750 and 1500. Whatever that result is, I take the greatest common divisor of that number and 1000. The answer is 250. Okay. So it talks about that briefly in chapter 2. If you want to see kind of a derivation of that, it's a pretty, in my view, it's a pretty useless skill to be able to use the greatest common divisor to identify a fundamental frequency. Much more useful skill is to do the measurement. All right. The world doesn't come with math functions defined on it. It comes with signals, and you measure signals, and you build the math usually from the signals. Okay. All right. So looking at this guy right here, we want to get it into this form, the sine and cosine form, because he looks like he's, why did I start with that one? Why did I start with the sine and cosine form? Why did I start with that? Doesn't that look like the most obvious one, right? How can I tell this one's the most obvious? What is it about that function that makes it the most obvious? What are my other forms, right? Well, my other forms are this shifted cosine and this complex. Does the shifted cosine seem like it makes sense for something like this? No. What do I not? What do I have? I have sine. I don't have any phase shifts in any of these terms. So without having any phase shifts in any of those terms, it makes sense for me to try to match it to this. So what we're going to do is try to pattern match, basically. Right? I want to try to look at what this function should look like, and I'm going to try to figure out which terms in this series appear in this function. Okay. So let's go through this. Do I have, so n equals, which one is the fundamental? I've got n equals 0 to n equals 7 here. Which one is the fundamental? What's that? 1. For n equal 1, right? So my frequency is n times my fundamental, so n times 250. The fundamental is 250. For n equal 1 is 250. What's this n equals 0 term? What do I call that? What do I call the n equals 0 term? DC term. And its frequency is 0. Right? 0 times 250 is 0. What's the second harmonic here? What frequency would that be? What's the second? Yeah, 500. Right? So the third harmonic would be what? 3 times 250. What's that? 750. Right? 750, 1000, 1250, 1500, all the way up to 1750. So, looking at this, which of these do I have? Which harmonics appear in this signal? F of this X, S of T is what this guy is called here. Which ones do I have? Yeah, I got a 4, which is 1000. I have 6, which is 1500. And I have 7, which is 1750. Which other one do I have though? 0. All right, it's got a DC term as well. So notice, I don't have to have a fundamental. This guy does not appear. This one doesn't appear. This one doesn't appear. That one doesn't appear. All right, so I effectively have 3 harmonics plus the DC term in this particular case. All right, so the fundamental doesn't necessarily appear there. Okay, it doesn't have to, but the summation of them repeats with that fundamental frequency. Okay, all right, so back to my steps. I found the fundamental frequency. I know which harmonic frequencies there are. Now I get to my third step, which is try to figure out what the heck the coefficients are. All right, so we said on the last slide, we had a 0 term. We had a 1500, a 1750, and a 1000. So we have those. Okay, so let's go through, starting with the fundamental. So going from fundamental down. All right, what's the coefficient A1 and B1? How much fundamental do I have? However, how much cosine omega naught t do I have to add in to match this function? How much would I have to add in? None. How much sine would I add in? None. All right. Same thing with the second harmonic. Wouldn't add that. Same thing with the third. Wouldn't add that. Now we said we've got something for 1000. Okay. Now looking at this guy, here's my A sub n and here's my B sub n. At 1000, I've got this guy. So at 1000, which terms do I have here? A or B? A, right? So this guy looks like I've got a 50 there, and I don't have any sine at that frequency. At 1250, I don't have either one. What do I have at 1500? So here's my 1500 term. What do I have there? Do I have an A? Nope. But I have a B, right? That's 2. Then my next one is this guy right there. Do I have an A on that one? No. But I have a B. What's the B value? 20. All right. Now, question is, what the thing that's always tricky for everybody is I did everything from the fundamental on down. I also have a DC term here. Okay. What's the DC term value? What should that work out to be? What's that? So first of all, looking at this formula right here, there is never a B0 term, right? It just doesn't have that. Okay. What's the A0 value? What's the A0? So where's the DC term over here? It's the 10, right? If I try to pattern match between these two, that tells me that the A0 value should be what? 20. Yep, 20. All right, that screws up a lot of people usually. All right, it's well, because if you look at this formula, and I didn't make the formula, right? In fact, I wouldn't probably do it this way, but the book does it this way. All right, so I'm just trying to be consistent with it. If I look at this, if I pattern match, if I say those two are equal to each other, then what I have is 10 equals A0 over 2. So A0 is 20. Okay. All right. That gets like I said, that will cause half of you to lose points on exam 3. All right. That always screws up a lot of people. All right. So if you look at the way you would code this into your homework submissions, what I ask you for is a vector, typically. All right. And I give you the form of the vector there, but there's no fancy coding per se. You could just sort of hard code this in where I basically say the first term here is my n equals 0 term. This is my n equal 1 term. 2, 3, 4, 5, 6, 7. You can match that with that table there and you can kind of see that pretty clearly. Okay. All right, so it's pretty easy. Again, what it'll ask you for in MATLAB is in the submission, it'll say, what's the maximum harmonic? In this case, what is the maximum harmonic that I have? What's the highest harmonic number? 7. 7 is the highest harmonic number. Okay. So the highest harmonic I have is the 7th. So I'm going to go from the DC term up to the 7th. Okay. So that's pretty straightforward to do. Now, what I ask you to do always is to say, okay, well, you just determine the coefficients in this series. Now I want you to go from the coefficients in this series to this one and to this one. All right. All three of them are equivalent to each other. But again, there's some times where one is more valuable than the other. Okay. All right. So how do I do that? Once I have the A and the B values, for instance, how do I get to the C values? That whole A squared plus B squared square root, right? All right. And the fact that in this case, theta is equal to negative tan B over A, right? There's a whole set of formulas, which I repeat here. So in this case, I'm repeating, I'm saying, all right, for a general nth harmonic, all right, I have these 4 versions, and I have these formulas over here that relate them. All right, now I've added one additional piece to kind of help me out a little bit, which is to say, if I looked at this guy, AN and BN, right? If I took those two things, this guy has a magnitude times a cosine. This guy has a magnitude times a sine. That looks kind of like the parts of a vector, right? So it looks like this guy becomes, if I told you C of n e to the j theta n. If I used Euler's identity to write that out in polar form, what would that look like? C times e to the j theta. What's that turn into if I use Euler's identity to write that in rectangular form? Yep, yeah, C sub n cosine theta n. And minus B C sub n j sine theta n. All right. So at least if I look at this, my A sub n and B sub n are parts of these vectors right here. Okay. And you can see where that comes from with this minus sign and that angle, right? If you go through that carefully, right? You'll see where that comes from. That said, this is going to be important to us in a little bit. All right. All right. Basically, what I've done up till now is I figured out the terms in this series. And now I can convert from one to the other. Okay. Just using these relationships. Not the most exciting thing in the world, but again, it's a lot more useful for me to be able to deal with the weirder ones like the complex and to be able to get to the more intuitive ones. Like the idea, and the reason I say it's more intuitive, hopefully it makes some sense, conceptually what we're doing. We're saying, all right, I can add up little sine waves to get to a square wave. It's probably not all that conceptually simple to say I can add 2 rotating vectors together that are complex to do the same thing, right? That's not an intuitive thing, but again, the math is easier with it. All right, so I want to keep going and try to figure out the rest of these now. So thing to remember before I can do that. So I talked about, okay, here's how I relate all the harmonics. Here's the thing with the DC term. Let's say I have a signal x of t equals to 10. All right. If I have x of t equal to 10, this guy here only has an n equal to 0 term. How would I, so looking at these, if x of t, I guess maybe I'll just call it f of t, right? If f of t is 10, so this guy is equal to 10, this guy is equal to 10, and this guy is equal to 10. In this case, I see A0 equals 20. What's C0 equal to? Looking at this form of the series, what's C0 equal to? What would that be? A0 was 20, right? I'm just pattern matching and I'm saying, all right, I've got just a DC term, right? So the DC term is equal to C0 over 2. So what's C0? Be 20, right? 20 divided by 2 gives me 10. In this case, my DC term is alpha 0, right? Looking at this guy right here, if I plugged in n equal to 0, what would this become if I plugged in n equal to 0? Become alpha n e to the j 0 omega t, which would become, this guy would become 1, so this just becomes alpha n. So what I see is that always the case when I get to become alpha 0. So what I have is alpha 0 equals A0 over 2 equals C0 over 2. This is the part that will cause you problems later. In two versions of the series, there's an over 2, and one of them there's not. All right. It's not, if you kind of think about it, it sort of makes sense because in these two forms, it takes two terms to always give me one component. Whereas this guy, sorry, in the complex version, I always have to have a positive frequency and a negative frequency together. At a frequency of 0, I don't have a positive and a negative. I only have one term. All right. Suffice it to say, all right, this is the relationship that I always end up with. And B sub 0 is equal to 0. Right? There is no B sub 0 term ever. If you look at it in the formulas, it doesn't exist. All right. So let me ask you this. If I have x of t equal to minus 10, right? And I said to you, what's the magnitude and angle of that? What's the magnitude and angle of minus 10? Right, minus 10. What's the magnitude of minus 10? It's 10. What's the angle of minus 10? 180. The angle of it's 180 or minus 180, right? Because it points in the negative real direction. Okay. The fact that a negative number has an angle sometimes screws everybody up, right? But if having a negative sign means that it has an angle of 180 degrees. Okay. All right. So what I want to do is I want to figure out what are the values of the coefficients here. Okay. Now this guy is actually not too bad to do, right? If I look at this, we had C sub n, if you go back to that formula sheet, is A sub n squared plus B sub n squared. Theta n is equal to negative tan inverse B sub n over A sub n. Now, this guy is actually easy enough that I can just do it by inspection. All right, so let's do that. If I look at the fundamental, I had no A and no B. So how much C do I have? Is there at any, if there's no, in other words, what that's saying is if A1 and B1 are 0, then I have no fundamental. So how much fundamental am I going to have in this series? How much is going to be there? Nothing. All right. And I don't have a second harmonic. I don't have a third harmonic. I did have a fourth. What's my C sub n value there? So A is 50, B is 0. So how much C do I have? If I plugged it into that formula, what would spit out? 50. Okay. And then I don't have anything at the fifth. I do have something at the sixth. What do I have here at the sixth? 2. And what do I have at the seventh? 20. All right, now I got to figure out the angles. Okay. So what are my angles? So yeah, well, so I'm going to come back to the 0 term, right? So I'm with the fundamental on down here, right? So the angle here, the way I look at this is I go in and I look at the vector here. So what I said was it's minus tan inverse of B over A, like that. So if I have 0, 0, the angle is going to be 0. If I have 0, 0, the angle is going to be 0. 0, 0, the angle is going to be 0. In this case, I have an A value, but I have no B value. What's the angle of that? So yeah, the way I said this is I always said C e to the j theta is equal to A sub n minus j B sub n. Okay. So if I look at this, for this guy right here, I have C4 e to the j theta 4 equals 50 plus j0. So if I had a vector 50 plus j0, which direction does it point? Real axis. What's its angle? 0 degrees. Okay. Don't have anything at 1250. Now here's a tricky one. 1500, I've got a B term. So I'm going to say I've got C6 e to the j theta 6 equals negative j2. What's the angle of negative j2? So where's negative j2 point? Straight down. So this is negative j2. What's the angle of something with that points straight down? Negative 90. Then same thing for the last one. Okay. All right. So it's not that hard to go kind of walk through and try to follow that process. Okay. What about the DC term here? Does the DC term, what's the angle? What's the angle of the number 10? 0, right? That's pretty straightforward. Could be 180. If there was a minus sign on it, it would be 180, right? What about the magnitude of C here? It would be 20 because it's the same as A0, okay? The actual DC term is 10. That means C0 is 20. All right, now, if I wanted to compute that, boy, that's awfully small. All right, that's me entering it in the way I would code that into MATLAB, okay, with those values. Now, if I want to go to the complex, how do I approach that one? Well, I've got all my values here, so you should know by now if the A's, the B's, the C's, and the thetas are all 0, those guys aren't there, right? So these terms disappear. How do I calculate AN? Well, alpha n was Cn over 2 e to the j theta n. And you probably have to go back to the formula sheet to remember, but alpha minus n, how does that relate to alpha of n? What do we say it was? It's the conjugate, okay? It's the conjugate, right? So it's pretty easy to sort of take those values and plug those in to these spaces here. These guys would go here. These guys would go here, okay? Now, what about the DC term here? What about the DC term here? Well, if I expand this formula out, all right, when I expand this formula out, what I end up seeing is the DC term, this guy is 10, right? Because I basically pattern match between these two, right? If I plug in my n values here, we said that basically this guy collapses into alpha 0. There's not an alpha 0 and an alpha minus 0. So this guy is 10. So if I look at that rule, what do I do? So A0 is 20, C0 is 20, alpha 0 is 10, just whatever the DC value is straight away, okay? And then I go through and I plug the formula values in for the rest of them, okay? So the formula values are there. At that point, I've gone through and done the whole thing. So how would I code that in MATLAB, right? This is how I would code that up. If you look, I created vectors, all right? And those vectors basically have entries for all the values in this table. So this was the DC term. then the fundamental, then the second, the third, the fourth, the fifth, the sixth, the seventh. Okay. Now, the alpha one is ugly. How many entries do I have in the alpha vector? 2 times as many, because I got values at the negative n values and the positive n values, right? So what I actually ended up doing, I'm going to talk about this more on Wednesday, but basically what I did here is I wrote out the positive values of alpha. And then I used this command right here. I could have written them out. If you're not comfortable with what I have here, you could write them all out. All right. But I have this command here, flip LR. Anybody know what that does? It flips the vector left to right. So whatever's last becomes first, and whatever's first becomes last. All right. They basically mirror over each other. Okay. And then I take the conjugate of it. And then I put this positive values and negative values, I put them together into one vector. And in between them, I sandwiched in the value for n equal to 0. All right, now, what I'll talk about next time is I just want to talk about a little bit of code stuff. All right, basically, how would I, you don't have to do this, but I can get a little bit more fancy with the code. All right, I wanted to talk about how I get a little bit more fancy with the code. Eventually, what we use is we're going to talk about how we would write code to basically graph this whole thing. So what I have is 3 of them, or all 4 of them, sorry, all 3 forms on top of each other. Okay, so we got to figure out that, but then we got to figure out what do we do if I want to calculate those values, not by inspection, but I actually want to calculate what those values are. All right, so we'll pick up there on Wednesday.